Welcome back to this session. In this session, we'll be starting a new unit, that is unit number 2. And the topic of this unit is simple stress and strain. And the weightage of this unit is 14 marks. So in this unit, we have to understand the types of load and what load means. So if we talk about loads are generally external forces that we apply on any member or any structure. If the force is applied externally on the member, those kind of forces are known as loads. So the types of loads acting on a structure for buildings and other structures can be broadly classified as vertical loads, horizontal loads, and longitudinal loads. The vertical loads consist of dead load, live load, and impact load. The horizontal loads comprises of wind load and earthquake loads. The dead load, now these are some of the loads that we need to consider when we design a structure. So some of these loads are dead loads, live loads, wind loads, impact loads, snow loads, seismic loads. These are some of the loads that we need to consider when we design any structure. So first, if we talk about dead loads, the dead loads includes loads that are relatively constant over time, including the weight of the structure itself and immovable fixtures such as walls, plastered board, or carpet. The roof is also a dead load. Building materials are not dead load until constructed in permanent position. So dead load generally consists of permanent loads, which comes under self-weight load or self-weight of the structure itself. So in self-weight, when we talk about self-weight, the weight of the structure, such as structural elements such as beam, column, slabs, walls, and then roofs, these are the structural elements of the structure. So these elements forms a permanent structure for that particular structure, and it forms a dead load. So next, if we talk about live loads are temporary loads. They are not permanent, they are temporary loads, and they are applied to the structure on and off over the lifespan of the structure. The most common types of live loads are occupancy load. So when we talk about occupancy load, we can talk about people moving in and out. Then there's things that we bring inside the building. For example, your table, chair, cupboards. All these things are movable, and hence they comes under live loads and under occupancy load. Then we can even consider the workers who are constructing the building and workers who comes for maintenance of the building. These are also live loads because they keep on moving. And other loads such as snow loads, wind loads, and seismic loads and impact loads. All these loads also comes under live loads because they are not permanent. They come temporarily. So a live load can also be expressed as a uniformly distributed load, UDL, or as one acting on the concentrated area, which is a point load. So next one is we have wind loads. So this wind load is primarily, it acts horizontally. So these are horizontal loads caused by the moment of air relative to earth. Okay, so wind load is required to be considered in a structural design, especially when the health of the building, when the height of the building exceeds 2 times the dimension transverse to the exposed wind surface. So normally if the height of the building crosses above 3 meters, then that time we need to consider the wind load as well. So generally wind loads are considered for multi-storied buildings, and for 2-story or 3-story it is generally not considered so much, but it would be better if you consider wind loads for those structures which are 3 meters above the ground surface. Okay, so the next one is seismic load. Seismic loads can also be known as the earthquake load. So this seismic load is the inertia force on the surface. It comes as the inertia force on the surface, and these loads are generally dynamic loads, which means that it brings about the vibration of the structure. Because when earthquake comes, it causes vibration. Along with that vibration, it vibrates the structure as well. So other loads such as dead load, live load, wind load, impact loads are generally act on structure very slowly and do not cause any rapid movements or vibration. So these kind of loads are known as static loads. But this seismic load, since it causes vibration instantly in a seconds of time, so these loads are not static loads. So hence the forces that comes from these seismic loads are different as compared to other kinds of loads. So next we have effects of load on a member. How the load affects any member or any structural member or any individual member. So when a load is applied on any member, it causes stresses, deformation, and displacement in a structure. So assessment of their effects is carried out by the method of structural analysis. So excess load or overloading may cause structural failure, and hence such possibility should either be considered in the design or strictly controlled. So we have to know how the load affects each member and when they are applied, in what kind of manner they affects. So the first kind of manner it affects any member is in a tension form. So how does a member will be in a tension? It will be under tension when the member is pulled in both the direction, in opposite direction. So you can see in this diagram that this member is pulled from both the sides, and from both the sides they are pulled in opposite to each other. The directions are opposite to each other. The force that is applied is opposite to each other, right? So in this case, this member is said to be under tension, and such member under tension will produce tensile stresses and tensile strain. So a very good example of a member under tension can be a tie member. Next one we have member under compression. You see this second diagram here. This diagram here is under compression. Now you can imagine a column. A column standing in a building will be taking a load from the beam and from the slab above, which is placed above the column. So beneath the column there will be a slab again, a floor, and above it there will be a roof, another slab, right? So a column in between will be sandwiched between these two slabs, right? The slab from top, which acts as a roof, and a floor at the bottom, which is also again a slab. So a column will be sandwiched between these two slabs, and from both the slabs there will be a force acting, or it will be pushing the column inside. So when it does this, when the column is under such condition, the column is said to be under compression. And when the column is under compression, it can produce compressive stress and compressive strain. So the other example can be a strut also. In this case, what happens? The length of the member which is under compression, the length will be decreased. So this is the small animation or GIF of how a member deforms when they are under tension and under compression. The first one that you will see will be under tension. So see, under tension it will be pulled and the length will increase. Under compression it will be pushed and the length of the member will be decreased. So next we have shear on the member. First we need to understand what shear means, what shearing forces are. So shearing forces are unaligned forces pushing one part of the body in one specific direction, another part of the body in the opposite direction. So you see here, these are two plates connected to each other with the help of a pin or a rivet or a bolt. It is here, you can see in this diagram, it has been connected, it has been made one with the help of a, let us say, with the help of a rivet or a bolt. Okay, now here this plate here, it is being pulled in this direction, and the other plate here, it is being pulled in the opposite direction. So when they are pulled in opposite direction to each other, there will be a force produced in between. There will be a force produced in between here, and those forces produced in between are called as shearing force. It will be acting along the plane, and these are known as shear force or shearing force. So as you can see here, only two plates are attached to each other with the help of bolt, and here the kind of shear that produces will be a single shear. Okay, and here you can see there are three plates connected to each other. Two plates, they are being pulled in one direction and one plate in another direction. So in this kind of situation, a double shear will be produced. A shear will be produced here, over here, where it is being held together with the help of this bolt here. So these pins, rivets, bolts are known as shear member. Because of these pins, rivets and bolt, it will try to hold the plates together in here, but since there is pull in both the direction and they are in opposite direction, a shear force will be produced in between here, and these pins are the members which helps in production of these shear forces or shearing in the member. So I hope this is clear. So these are some of the diagrams of, these are pins, these are bolts here, these here are rivets, and all of these are shearing members. So next kind of force that comes on a member, especially on a beam, is known as a flexural force or flexural strength. Okay, so when there is a beam here, and when a load acts on the beam, this beam will start bending. It will start bending. It will start bending in this manner. So this, originally we have this beam here, and when a load is applied from here, this beam will bend, and when the beam is bent, there will be a bending stresses and strain produced, and these bending stresses are the stresses that are developed in a beam or any structural member due to pure bending. So if there is a pure bending, bending stresses and strain will be produced, and this kind of member are said to be under bending action, and we can call this member as a bending member, or we can even call this member as a flexural member, and beam is the best example for this kind of member. Next we have effects of member due to torsion. Now consider a shaft. If you don't know what shaft means, shaft is a long, narrow part or section forming the handle of a tool or club, the body of a spear or arrow or similar kind of member. So as you can see here, this is a long body. It kind of looks like a spear or an arrow, right? So this kind of body, when a force is applied, you can see a force is applied in this direction, this one here, It is applied in this direction, right? So when a force is applied in this direction, this force produces a twist. It twists this member, and when the member is twisted, this whole member is said to be under torsion. So a good example of a member under torsion is a shaft. So some of the commonly used engineering materials are mild steel. So mild steel, they look like this. Very they are very plain, and as you can see, this is a torr steel. This kind of steel can take more tension forces and as compared to the mild steel. Aluminium, copper, concrete, bricks, then tiles, stones. These are some of the commonly used materials for building a structure. So the materials, all these materials will have some properties, and these properties are mechanical properties, thermal properties, magnetic, electrical, chemical, physical properties. Now, from all these properties, for us civil engineer, we are much obliged to know more about the mechanical properties of those materials. So first, let us know the different classifications of material. The material can come under many different classifications, such as elastic, plastic, ductile material. So all those are classifications of material. And let us first know what elastic material means. Elastic, if a body possesses an elastic property, it has the tendency to recover to its original configuration or original shape and size when we remove the deforming forces, right? So as you can see in this diagram here, in this diagram, a force is applied on a rubber band. And when I remove the force from this rubber band will come back to its original shape and size. So this kind of material are known as elastic material. Next we have plastic material. In plastic material, when we apply a force on a plastic material and remove that force, it will not recover back to its original shape and size, but instead it will break and go into permanent deformation. So such kind of material are known as plastic material. And the good example of this kind of material is clay and lead. Next we have ductile material. To understand what ductile material means, we have to understand what ductility means. So ductility is the physical property of a material associated with the ability to be hammered into thin and stretched wires without breaking, right? A ductile substance can be drawn into wire. So a ductile material, it can undergo a huge deformation without them breaking. It can form into a thin wires. It can be drawn into thin wires, and if it can be drawn into thin wires, those kind of materials comes under ductile material. So a ductile material has a large tensile strain up to the point of rupture. And the very good example of this ductile material are mild steel, copper, gold, platinum, silver, etc. Mild steel, it is because this is the reason why we use mild steel in construction, because they can take a good tensile strain. And ductile material must be both strong in elastic as well as in plastic section. And before failing, this ductile material gives a failure significance. It gives a warning. Next, we have classifications of material again. Brittle material. So this brittle material, a material is brittle when subjected to stress. It breaks with little elastic deformation without significant plastic deformation. So brittle materials absorb relatively little energy prior to fracture, even those to high strength. Breaking is often accompanied by a snapping sound. So in brittle material, what happens? Like I said, that if when it is subject to a stress, it breaks with a very less elastic deformation. So this kind of material are known as brittle material. Then a brittle material fails suddenly upon attaining its maximum load and has a small tensile strain up to a point of rupture. So the example of such material can be glass, cast iron, stone. So best example is the glass for you to understand. Next, we have strength. What does strength mean? So the ability of a material to resist its failure under the action of load is called as strength of the material. So when we apply any kind of force on top of the material, and if it is able to resist those load and resist its failure under the action of load, that means the strength of the material is more. When we apply a certain load on the material, and if it breaks suddenly when we apply that load, that means it is not able to resist those load. If it fails suddenly, we can say that the strength of this material is less, right? So material should have sufficient strength when subjected to tension and when it is subjected to compression, bending, and shear and torsion. So it should when the material is pulled, or when the material is pushed, or when the material is under shear and torsion, it should be able to resist all these forces. Then we can say that this material is strong. It has a high strength. Next, elasticity. The ability of a material to regain its shape, as we have already covered. Elasticity, if the material can regain back its original shape and size, the material is said to be elastic in nature. Next, we have stiffness. Now, if I define what stiffness means, it can be defined as the property of a material which is rigid and difficult to bend. Difficult to bend. Now, if I say that, what is the stiffness of this material? I'm trying to bend it, it is not bending, right? So it is stiff. It is difficult to bend, it is stiff. So the stiffness of this material is high. I can say that, right? The resistance of a material to elastic deformation under the action of external load is called as stiffness, right? The degree of stiffness is indicated by modulus of elasticity in case of tensile stress and compressive stresses, and by modulus of rigidity in case of shear stresses. So if we have to know stiffness of the material, and if the material is undergoing tension and compression, its stiffness is represented by modulus of elasticity. And if the material is undergoing shear stresses, its stiffness can be signified with the help of modulus of rigidity. Next, we have mechanical properties of a material. Again, plasticity. You again know what plasticity means. If a load is removed from a body, and if the material does not regain back its original shape and size but goes into permanent deformation, those kind of materials are known as material will possess plastic mechanical properties. Next, malleability. So malleability, it is the property of a material by virtue of which it can be beaten into thin sheets without cracking when hammered. So malleability, in malleability, what happens? Malleability, please do not get confused between malleability and ductility. In malleability, when you hammer or when you apply force on any material, and if it can be drawn into a thin sheets without cracking, without taking much indentation, or without taking much of the effects from the hammering, then those kind of material possess a malleability property. And the good example of them are gold, right? Gold, if we have a lump of gold and if I want to make a earring out of it, I can draw them into thin sheets, and then I can make a gold earring, right? I can make chains, I can make into any shape. So gold is the very, very good example of malleability. Next, we have ductility. In ductility, if the material can be drawn into thin wires, so when we put a force on any material, and if it can be drawn into thin wires after hammering, after putting a force on it, then those material is supposed to have a very good ductility property. And the example is again a mild steel, copper, aluminium, gold. So these are the example of ductility. Brittleness, again, if a load is applied, if a stress is applied to any material, and if it does not take, it will not be able to take enough stresses, and it will fail. It will fail directly. So those kind of material are known to have brittle property. So in this case, the material will fail before giving you any warning. So good example is a glass. Next, we have hardness property. The ability of a material to resist wear and tear, scratching, aberration, cutting, or indentation is called as hardness. Now, hardness, how you can imagine a tire. A tire, it runs on a road so many times, right? So it will resist all the wear and tear, scratching, aberration, indentation that is coming from the road. And a good tire will have a good hardness, which means that it will be able to run for a longer period of time. And when it starts wearing and tearing, the tire will no longer be used as a good material. So we'll have to replace that time. So tire can be an example. And other best example is a diamond. Diamond is the hardest material available on earth, right? So if you hammer a diamond, you will not be able to break it, or you will not be able to scratch it, or you will not be able to produce a resistant you will not be able to produce wear and tear in the diamond. So we can say that diamond has a very, very good hardness property. Next, we have toughness. Toughness means when we say I have a stone, then I'm suddenly applying a huge force on the stone. Now, before this stone breaks, I'm applying a force. When I apply a force, the stone will be absorbing all the forces from the hammer and it will break. So before it breaks, the amount of force it absorbs is known as the toughness of the material. So toughness of material decreases with heating of the material. Now, the same stone, I take it, I heat it, and I apply a force on it. the stone will become brittle in nature, and it will break quickly. So it becomes toughness is reduced when it is heated, when the material is heated. Next I have fatigue. Now what is fatigue? Material fatigue is a phenomena where structures fail when subjected to a cyclic load. It means cyclic load means repetitive load. This type of structural damage occurs when the experienced stress range is far below the static material strength. Fatigue is most common source behind failures of mechanical structure, right? So mechanical structures such as axles, springs, shafts, connecting rods, etc., they undergo a lot of repetitive loading conditions or repetitive load. So when it goes under repetitive load, it will fail. It will fail, and that failure is caused due to fatigue. Fatigue property of the material. Next we have creep, right? This creep is defined as a time-dependent deformation when material is under constant loading. So generally the structure, when we say that the structure's lifespan is 50 years, it means that in 50 years time the creep will be forming, and in 50 years time, because of the creep, there will be a deformation in the structure. So creep is totally a time dependent property or time dependent mechanical property of a material. So the continuous deformation of material which undergoes with time to apply it to the application of external steady load is called as a creep. There are different types of bodies here again. There are three types which we have already covered: elastic body, plastic, and rigid body. So practically, if we see outside, rigid body is assumed to be no body is rigid, but they are assumed to be rigid for engineering applications. So these are types of loads. Under types of loads, you will have direct load, eccentric load, shear load or shear force. And under direct load, you will be having tensile load and compressive load. So in types of load again, direct or axial load can be defined as applying a force on a structure directly along the axis of the structure. So you see, let me draw one diagram and explain it to you. I have a member here. And let us say that its y-axis is running from here, y-axis. Now along this axis, if I apply a load, I'm applying a load force F here. So if I apply a load directly on its axis, this kind of loads are known as direct or axial load. So direct load always act at the centroid of all cross section. So here, centroid, somewhere around here, so it will act directly at the centroid. It is further classified into two types as tensile force and compressive force. So let us further look. So we have tensile force here. So in tensile force, as I have already explained, if a member is under tension, it will be pulling the body in two opposite directions, and hence the length of the body changes. So you can see here that this is my axis. Here, this is my axis of this member here, two axis, and this load is directly applied along the axis of this material. So when it is being pulled outside, it is directly acting from the axis of this member, and such kind of forces are said to be tensile force or tensile load. Next, we have compressive force. Again, along this line, this plane, this is my line of axis of the member, and here the force is acting inwards, hence putting this whole member into compression. So you can see here again this axis, and the load is directly acting on the axis, and this time it is acting inward, and hence this member will be under compression, and the body will be subjected to compression and causes decrease in length of the body. Next, we have eccentric load. Now here eccentric load, this line here is my axis of the column, and along the axis, if a load is acting away from the axis, then this distance here is known as the eccentric distance, and this load so produced at this point here is a eccentric load. Okay, so when a load whose line of action do not coincide with the line of action of the body, then it is called as eccentric load. Here, this load which is applied here does not coincide with the line of action of this member here, so hence the load which is applied away from the line of action of the member is known as eccentric load. It always acts at an eccentricity E from the centroids of all cross section of the member. So the eccentricity E is here is the distance. Eccentricity E is the distance from the line of action of the member. Next, we have shear force or shear load. So when a force acting along the plane of the area of a body is called as shear force. Example, you can just take an example of a bread. You have a whole bread, and let us consider this a whole bread. Now I want to cut from this plane here. I want to have this much slice. So when I put a knife here, the knife will be acting from this plane here, this plane. So when I put a knife along this plane, there will be a resistance. This part where I'm holding it with my hand here, I'm be applying a force here with the help of my hand. This part will be pushing upward when I apply the knife downward, right? So there will be action, two forces going in two opposite direction. One will be going upward, one will be coming downward towards the slice. So in such cases, a shear force will be produced. Example is cutting the bread by a knife into slices, right? So this is the example here. So today in this session we will stop here. We'll continue our session for the next class from slide number 34.